All right, good morning, everyone. This is, okay, so first off, exam next class period, right, Friday. Recitation today, just like for the recitation prior to exam one, it's just going to be a review session, so please bring your questions to the review session. Show up whenever you want, leave whenever you want. You don't have to show up at all if you don't want, so whatever is really there just for help if you think you need it. So I'll be there from whatever, 3 to 6:15 or whatever it goes to. Okay. This was when we ended class on Monday. We had gotten through drawing the root locus for this particular problem. This is essentially what the root locus looks like. We talked about with the previous example where the poles go, and here we're going to talk about the same thing here as well. So what we see, or what we can glean from this root locus plot here, is a few things in terms of what we have to worry about, or what's going to be the dominant response of the system. So first off, if we look at performance and what we have to worry about here, we're going to have one branch associated with one of the poles here. We had a double pole at -4. One, as k increases, is going to keep on moving to the left. So let me use a different color. That didn't show up very well. Maybe this will be more distinct. All right, so we're going to have one pole, closed pole is going to keep on going to the left. In general, we don't have to worry about what's going on with that pole in terms of performance, because we said from previous lectures, as the pole is farther into the left-hand plane, it becomes less and less consequential in terms of the total response. So this one's continuing to move on to the left. It's not going to be a major concern in terms of either stability or performance for us. We have another branch of the root locus, and it's going to have a closed loop pole associated with it. And as we see, we're going to get a movement as k increases, where that pole is going to move towards the open loop 0 of the system. And then trying to tie things together here between content from a few weeks ago and in this specific example, what did we say about the open loop zeros and their association with closed loop zeros? This was a homework problem that we went through. It was one of the things that we talked about. I remember that, I forget, it was homework 7 maybe? No? No one remembers that problem? Yes, they have hand count up.
The zeros of like your planet, you can't ever get rid of them. No matter what you close.
Yeah, exactly. So feedback, which is what this whole last half of this class is about, allows us to move the poles. We have a planet with some, we'll say open loop poles. Feedback allows us to move those closed loop poles around in the complex planet. Right. So that's the benefit of feedback, but it does not actually allow us to move the zeros. So if we have zeros at position, in this case, the position of the zeros at -1, there's going to be a 0 in the closed loop system at -1 as well. Okay, so those will not actually move. And so how we should be interpreting this is that we have a closed loop pole along this branch. All right, where'd my marker go? There it is. All right, so we have a closed loop pole along this branch. As k gets really, really large, it's going to move to this 0, which is an open loop 0. It's also a closed loop 0. And so we're going to get a pole 0 cancellation as this pole gets closer to this 0. Right? There's actually going to be a cancellation, where the effect of the pole closest to the origin is actually going to go away because of the cancellation here. Yes? Okay, so yeah, so kind of as a doodle here, if we have, all right, so we have, when we talk about root locus plots, we're talking about a generic transfer function G, right? And so, since this is a transfer function, it has poles and zeros associated with it, right? And so if we want to say, all right, where are the open loop poles and zeros of the system? I'll put a gain k out front here because this is going to be in the form of what we're talking about. But a gain does not add poles or zeros, it's just a gain, right? It does not change the solutions of the numerator denominator. Right? And so if we talk about open loop, that would be just this system here, no feedback, right? And so we can figure out what the poles and zeros here are just by looking at the numerator, denominator, say them equal to 0, understand what the values of S are such that that's true, right? When we say closed loop, what we mean is that we have now closed the loop by putting all the hardware in place to actually perform this action of closing the loop. And now we talk about closed loop zeros, closed loop poles. We're talking about this transfer function, C over R. Okay. Right. But then what we learned in the one homework problem is that if we have a set of zeros of G, those zeros are also going to be in C over R. Not the case for poles. Okay. So the root locus here shows us all the potential values of those closed loop poles, and we're saying that as k increases, the closed loop pole along this branch is going to go, and it's actually going to cancel this 0. So the effect of this pole really close to the origin is going to become nullified. Yes?
So the open loop is pretty much just your k times g, and your closed would be like k times g over 1 plus.
Exactly. Yeah. So yeah. So OL is k times g. Closed loop would be kg over 1 plus kg. Yes? So, yeah, so there's, yeah, that's a simple way to discuss it. So the more correct way to say that you have a set of open loop poles, or sorry, open loop zeros. Closed loop zeros would be, those would be a subset of the closed loop zeros. Okay. So if you have open loop zeros, those will always appear in the closed loop. You could have extra ones. It's coming from so here's what we talked about. Here's the solution to this homework problem that we went through. So if we have so we have zeros of the controller, that's A of S. We have zeros of the plant, that's N of S. If we could look at the closed loop, it includes zeros of the controller, zeros of the plant, and also zeros or poles of the sensor. So if we have a sensor here, it's going to add extra zeros, but we don't have that in this case. Okay. All right. Any other questions about these two branches of the root locus? Ben.
So, like ideally, say you're increasing k in this situation, you still wouldn't want that cancellation, right? Because your system would probably be unstable because it crosses within the right-hand plane of your other pole.
Okay, yeah. So, yeah, so just to rephrase that a little bit, if we wanted to get a perfect cancellation, that would mean we have to increase k to be infinity, right? And so you're saying that we have two branches here that if we increase k to be infinity, these closed loop poles associated with these two branches will be in the right half plane. Yeah, exactly. So yeah, so that's a good segue into the next point is that we have these two branches. This is where the closed loop poles move as k gets large. So if we increase k too much, eventually we're going to find a value of k such that the closed loop poles are in the right half plane, right? So if we get perfect cancellation, you have to have k is equal to infinity here. That's not going to be possible for this specific system. Okay, so in terms of things that we have to worry about here, we don't have to worry about the closed loop pole here going unstable. It's going to terminate at the 0. We do have to worry about these closed loop poles associated with these branches here. All right, so if k gets to be too large, our system will go unstable by this analysis. Any questions on that general kind of math concept that we have here? Okay. All right, so a good question whenever we talk about this is at what value of k, at what value of k will the system go unstable, right? So if we're trying to understand what are all the possible gains I could choose in my controller by modifying this by software, it's good to know what would be a really bad choice, right? And what would be an allowable choice that's going to be safe, right? So the way in which we can do this, we can use the same rules that we say dictate the root locus. We can use these rules. This is going to, as a reminder of what the two rules are that define our root locus. Is we have this angle criteria, which is basically how we built everything for all the rules applying the root locus, or built out this angle criteria. And now we have this gain criteria, which can allow us to understand and find some unknown k for closed loop positions S. This idea. So think of these two equations as kind of your main tools for understanding or designing systems with root locus methods. Okay, and we'll get into design more in the next lecture, but this is these two are going to be the two equations you're going to use all the time here. Okay, so what this is saying is that if you have some sort of value of S and it's along the root locus, so we have, say, magnitude of g of S, which we can write as this equation here on the right. If we have some value of S that's along the root locus, we can write this expression where it is composed of all the magnitudes of vectors running from the zeros to that value S, all multiplied together, over magnitudes of vectors running from all the poles to that value of S, also multiplied by the inherent gain of the system, and that's going to equal 1 over k, right? Which is k is this variable we're varying from 0 to infinity when we plot the root locus plot. Right. So what we're saying here is if I want to know at what value of S, or what value of k, I mean, that we have a pole that is teetering on the brink of instability. So by that, I mean, what is the value of S such that the closed loop poles are exactly on the imaginary axis, right? This is the cusp where I go from being stable to unstable, right? So this is going to be what I'm going to try and use as a test point to understand what is the range of k such that my system is going to be stable. Is that any questions on that thought? Okay. All right. So we'll call this here. This is at a value of k equals k critical, right? So the system is going to be stable for k less than k critical. Let me put this a little more formally. This is kind of sloppy here. So as k increases, the two complex conjugate poles cross into the right half plane. This happens at k is equal to k critical. So then the stable region is for values of k that are between 0 and k critical. So the question is, how do we find this critical value of k such that our system is going to be stable? And we're going to use the magnitude rule that we just saw a second ago. All right, so that rule, I just had it on the previous slide, but I'm going to show it again. The magnitude of g of s is equal to 1 over k. Or alternatively, if we want to solve for k, that equals 1 over magnitude of g of s. So magnitude of g of s, from the previous pages of this lecture, is the inherent gain of the system over then the product of all the zeros, of the vectors going from all the zeros to that test point S, to then over the product of a bunch of vectors going from the pole locations to that test point S. Okay, so we know that, and this is, again, this is coming from an approximation here based off of our drawing, but we know that a pole pops into the right half plane at a value of S approximately equal, and here this is what we're going to say is somewhere around, just to use nice round numbers. Yeah, so use nice round numbers, somewhere in a value of 5. Okay, so to get an approximate value of this k, right? So, and this is S is approximately equal to 5I, right? Is when this happens. So this is going to be your test point. This is our point of interest, right? This is where we're right on the cusp of our closed loop pole being unstable. And so when we're writing this, we are going to say our gain of our system in this example is 1. That's coming from the problem statement. But we can look at a vector running from all the zeros on our system to this test point, and we'll use orange. Hopefully this doesn't look too much like the red color. All right, so this is the magnitude of this vector going from our 0 location to this point. All right, and if we look at this, this is a vector with real part of 1 and imaginary part of 5. And so via Pythagoras' theorem, we can figure out what the length of this vector is. In the denominator, we have 4 poles. So we're going to have 4 of these vectors. We have one running from the origin on up. This is going to be a vector of magnitude 5. We have another one going from a pole location of -2 to that point. This has a real part of 2, imaginary part of 5, and then we have 2 vectors, because we have a double pole here, with a real part of 4, imaginary part of 5. And we have 2 of them, so this is going to be squared. All right, so if you were to throw this in a calculator, you would see that this equals to 0.046. That means that K equals approximately, and we'll say approximately here, because we just read this off the plot to the best of my drawing abilities, approximately equal to 216. All right, so we'd say that the stable range for the system is K between 0 and 216. So this tells us that we can increase our gain up to, say, 200, and the system still should be stable, right? This is, again, approximate, so we probably shouldn't go and push it to, like, 215 or something like that, because I just read this off the plot. This gives us a general idea of what range the system is going to be stable when we have feedback with a simple proportional controller. Yes?
Doesn't it also oscillate like really crazy and then dim out? So if we were going to use this maybe in a robotic system, there'd probably be like a factor of safety or something associated.
Yeah, exactly. That'll actually be the next example. Here we're just saying, all right, baseline, we need to show that it's stable. We'll talk about performance as soon as we get through this little sub-example. We'll talk exactly about your question here. All right. Sorry? Exactly, yeah. So it's going to be exactly the same procedure. Instead of looking at our test point of interest, being right now it's when it crosses the imaginary axis, we're going to look actually where it crosses, I forget what happens in this example, but it's either when it crosses a rise time constraint or an overshoot constraint. So. Okay. All right. So that is from kind of just looking at it from hand-drawn tools. If we look at this in MATLAB, there's tools that we can use here as well. So yeah. It will not always be 1. So the reason why it's 1 in this case is the problem statement. So let's go back to the problem statement. So here's the problem statement. This is G of S. So if, for instance, I were to give you a different problem statement where this is, say, 5 out front, that would be the inherent gain system. Okay. So we have G in this case is ZPK. We have a 0 at -1, and then we have poles at 0, -2, -4, -4. All right, so here's our transfer function. We can use our locus if we want. This is, I would say, the easiest way to get a root locus plot, or fastest way to get a root locus plot. Okay, showing essentially the root locus plot we just drew. And then if you use these data cursors, usually when you use data cursors in a MATLAB plot, it just tells you basically its X and Y position. And here, oh, look at that. So here we're a little bit into the right half plane. Let me move to the left. So this is kind of down to the resolution of this plot here. So to the left, it's a gain of 182 is at this location, and to the right is 216. Right? And so we calculated by hand 216 exactly, actually. So we were pretty close. But this tells you at what gain your system will go unstable, right? Right here. It also gives you some other things. It gives you pole locations. It gives you the damping of that pole. Gives you overshoot, etc. So you can see how, as I move this around, all these damping values, overshoot values, frequencies, etc. change. So this is using the tool RLocus. Yes?
Is there a way to get rise time on it?
Not with this tool. With as far as I'm aware, but the CISO tool would do that for you.
Okay. Can you increase the resolution anyway? Like tell it to.
Not that I'm aware of. Yeah. CISO tool does a better job of that.
Okay.
Yeah. This is, I'd say, like the quick way to get a good locus plot. Okay, so this is one tool you can use. This is if you want to get a locus plot really quickly to check your work. If you want to put a little bit more effort and have, but then also have a lot more tools available to you, you can use CISO tool. All right, so the advantage of CISO tool is it also shows you where all the closed loop poles are simultaneously. So as a recap from previous lectures, the pink squares here are the closed loop pole locations. So this is for, the default is a gain value of 1, so a gain value of 1. The pink dots are all the closed loop pole locations. I can then move these around. Computer's being very slow these last few days. I don't know why. Move. There we go. All right, finally starting to move. Okay, so you can see how these are all moving as I increase this value k. You may ask, how can I tell I'm increasing this value k? If I go to and understand what is my controller, C, I can actually type in specific values of k. So I want to say, all right, I want to understand what the closed loop pole locations are for a gain of 100. It'll automatically update where these closed loop pole locations are. So Ben, getting back to your question, you said that, all right, we have to increase the gain to infinity to have this a perfect pole zero cancellation. And you said that if I increase the gain too much, these poles are going to move in the right-hand plane. You're exactly correct. But you can see even for gains where the closed loop poles have not gone into the right-hand plane, you still get an approximate pole zero cancellation here. And so then if we increase the gain to what we said it was for instability, 216, we see that was essentially right in the cusp of being unstable, right? And then we can check this with the step response. We see this blows up to infinity. If I dial the gain back just a little bit, say just at 200. All right, so stable, and that this is defined by converging exponentials, but as mentioned, this would probably not be favorable performance, right? So we'd have to, once we establish this is stable, then we could modify things from here. And then this is just to make sure everyone's on the same page, this is just barely to the left here. This is right on the cusp of being unstable. Okay. All right. Any questions on that idea? Okay, so everyone I think realizes why this is bad performance. We can talk about what would be a better performance. So if we have our software tools we can use here, we can start to add, say for instance, if we want to limit the overshoot to be, let's say, 15%. All right, so this is going to put markings on our plot for us, showing what is, if we call the yellow region a exclusion zone, so we want to make sure that no closed loop poles are in this region. This gives us an idea of where the closed loop poles should be. So via the software tools, I can just move these such that they're inside. Now you notice that we don't have as well of a pole zero cancellation here anymore, so we're going to have aspects of our response that look somewhat like a first order response, because that's what a real pole looks like. But we see that we're going to have significantly lower overshoot in this example, because all of our closed loop poles are in this region that we say we're going to get less than 15% overshoot. And if we look at our step response, we get actually no overshoot in this example because of the action of that pole at the close to the origin. Actually, it's causing a fairly not perfectly first order response, but it has aspects of this exponential response that you get with the first order system. All right. So this is, I would not call this quite into the elements of what we'll say with design. We're going to design, by design, controller design, we're going to be designing poles and zeros of the controller. This is more just designing a proportional controller to have a favorable response for the system, but we can use some of the tools that we've been building up to understand where should the closed loop poles be to get a response that we want, that we think would be favorable for the system. Yes?
Can you change the KPKI and KPKB coefficients?
Sorry?
Can you change the proportionality coefficients between the PI and B terms in this tool?
Yeah, you can. So yeah, we'll go through a lot of examples of that, but you can add, if I go back to my controller, all right, if it ever decides to pop up. Probably have it open already. There we go. Okay. So here we have they call a controller compensator. These are interchangeable terms, controller versus compensator. Right here you just have a static gain, which is 32. It doesn't really matter too much, but that gave us the response we're showing last. We can add dynamics to this. If you right-click in the box called dynamics, you can say add poles and zeros, and I can add an integrator if I want. I can add, now integrators can make the system go unstable, so be careful. I can add a differentiator to the system. All right. And all these other things, and we can add, what we're going to mostly be talking about is what they're called lead lag controllers. We'll get to that in the next lecture. But a lead lag controller has both a zero and a pole associated with it. And we'll talk about that a lot in the next lecture. But these are dynamics we can add to our controller. And then the proportionality between all of them would be this gain out front. So I could say change this to 25 or whatever I want to modify. And it's going to update everything. It's going to update our Bodie plot. It's going to update our step response for Locus all automatically for us. Okay. Any other questions about this example? So I wanted to do a quick little exercise kind of following along these ideas. So let me pull up an example of that. So this is from a midterm I gave a long time ago. Just to note, this content is not content for this is not content for the upcoming midterm. This would be for the more applicable to the final exam. Sorry, 1 second. My wife wants to know if I fed the dog this morning, so to prevent my dog from going hungry, I'll respond. So, okay. So this problem statement. So we're just going to go through this. This is leveraging the ideas that we just had here. So I hope this can be visible in the back. Can you see the plot in the back? Okay. All right. So this problem is asking it in 3 different parts. Okay, it says that you have what's essentially a root locus. This is a root locus plot for the system here. And it gives you the transfer function with all these funky numbers, and the numbers don't really matter. It's more of a red herring, all these numbers, but it says, all right, for what values, or what range of values of k is the system stable? it gives you a bunch of dimensions on this plot, and we're trying to understand then, from the dimensions on the plot, what values of k is the system stable. We'll talk about part A first before we get into part B. So I want you to take 5 minutes, think about what we just did for this last example in terms of drawing vectors between all our pole locations and some sort of point of interest, and see if we can come up with what values of k the system is going to be stable for, kind of leveraging what we just talked about. So we'll reconvene at about 40 after, talk about this, and then we'll go through parts B and C. So A is a little bit more using the tools that we just saw. B and C are a little bit more conceptual in nature. Sorry? Okay. Should put up a good sweat then there. Yes, Ben. Sorry? How high H is? Just use everything in terms of the variables on the plot. Everything is a dimension of the plot. So H is a vector. Okay. So I think most people went from pointing at the board to now talking about other things. So we'll talk about this problem here. So who has an answer they're comfortable with? Huh? No. From the variables on the plot. Oh, you did it with calculator? Okay. Yeah. Okay. Actually, Thomas, you had the answer, right? No, that's right. I forgot. This is the reason why I don't use the regular PDF editor. That the erase doesn't work so well. So the answer is. How does this work? Okay. Let me open this up in a different program that doesn't suck terribly. All right. Okay, so the answer is that K is between h squared E F over B. So then the question is, why is it this? All right, so Thomas, why is it this range here?
Because K causes the system to go unstable when any of those poles crosses the real axis or crosses the zero axis of the right-hand side. So there's a really convenient point on the upper branch where there's a bunch of nice, happy vector magnitudes marked out for you.
Right there? Yeah.
So you have vectors from the double pole at the roughly origin.
Yeah, so if we were to say what G of S is, or magnitude of G of S, for Thomas's selection of S, you would say from this vector coming from the double pole, you have a H associated with the first pole of the origin, then you have two of them, so that's H squared, right?
There's an F from the magnitude bottom, the pole, the other half.
Yeah.
And there's an E from the top one. And then there's a B from the zero.
Yeah, so 0. So then the length of the vector coming from the 0 to that position is B. And so we know that K for this, the K to achieve this closed loop pole location would be 1 over magnitude G of S. So then we just flip this here. So that means that the K, as long as between H squared, between 0 and H squared EF over B, then we know system's stable. So there's a very geometric way in which you can interpret these root locus plots to try to understand what the value K should be. This is mapping back to some of the homework problems that we did associated with lecture 2, which would have been homework 1, right? So I hope something's all coming together here in terms of all these terms here. But so you can look at a root locus plot. You can actually just draw out vectors. You don't have to have any numbers. If you had like a ruler that was pretty accurate and you had a graph that was drawn to scale, you can actually get this purely from geometry of the system. So part B here asks, all right, how would the shape of the root locus change if instead we drew the root locus plot for G hat, if G hat is 5 times G, right? In what ways would the root locus plot change, or the shape of it? Okay, so we have one person says expands. Anyone saying contract? Anyone say doesn't change at all? So we have one expand and a bunch of people abstaining from voting. So K critical is going to decrease actually. But the question is, how does the shape of the root locus change? Yeah.
Wouldn't it just like shift everything along the lines where the
Sorry.
would it like, so if this is for K is 0, right? Like where these plots are shown, would it just like shift them along the lines or no?
So this is showing the critical value of K, which the poles go up to the right hand side. But the shape. So if I were to plot this, the root locus plot to 5 G of S with these blue lines, the locations of all the blue lines.
Would it not change because the 5 wouldn't affect your poles or zeros?
So the answer is that it doesn't change the shape at all. Okay. So you're right. So it doesn't change the pole or zero locations, right? So if I take this transfer function and I instead multiply it by 5, the poles and zeros of this transfer function did not move. Right? And so then there are two ways to think about why the shape doesn't change. The first is that all the rules that we went through for plotting this are all based off the number of poles and zeros and the locations of poles and zeros, right? So since we didn't change either the number of them or the locations, then we wouldn't expect the shape to change. The other is actually going back to the definition of the root locus. So the definition of the root locus is all the closed loop pole locations of, or roots of 1 plus k g of s is equal to 0 as k ranges from 0 to infinity. Okay, so if we say also, what would all the values of 1 plus kg of s equals 0 be if we now say this is 5 g of s? This range of going from 0 to infinity, if we multiply that by 5, 0 times 5 is 0, infinity times 5 is 0. It's still the same exact range, right? Exactly. So then going back to the discussion about, all right, at what value of what would be k critical be, that would be 5 times less. Or 1 over 5 times that value. Okay, so even though the shape won't change, the closed loop poles will move along the root locus 5 times as fast as we modify k. So the critical value for part C here is that k would be in the range of h squared EF over 5D. Right. So your system is going to go unstable at a lower gain, but the shape, in terms of its trajectory, is not going to change at all. Okay. Any other questions about this more conceptual problem with the root locus plot? Okay. Yes, Justin.
So is that saying that like the point that you have circled where that like asymptotic line goes through the imaginary axis, that point is just like 5 times less?
So the point in the complex plane is exactly the same. So there will be a closed loop pole that jumps from the left half plane to the right half plane, exactly the same location. The gain required for the pole to be at that intersection of the imaginary axis is a factor of 1/5, the original system. Okay. So just kind of bring this all together here. If we look at what is magnitude of, say, G hat, this would be equal to 5B H squared FE. And that's why when we said over this other case, this is 1/5, the original answer. Okay. All right. So we have 4 minutes left in this class. I don't think it makes sense to start a brand new lecture. So any general questions about the exam on Friday? I really can't do an example problem in 4 minutes, but anything in general about the exam? Yes.
2 questions again.
It'll be 3 questions this time. But if we look at exam 1, I forget which one was the long one. There was a long problem and a short problem. All right. This time it is 3 problems. They're all, I would say, on the shorter end. Yes.
Is root locus going to be covered? Is like everything covered until?
No, only for homework 8. Okay. So nothing in the root locus.
Are we going to do like physically draw any block diagram or like derive stuff from like a picture of block diagram?
Yeah, so that's fair game, yeah.
In a nutshell, what is it all covered? Does that go over electromagnetism and stuff like that still?
So if you look at kind of exam 1, basically went through electromagnetism and we got through moving coil transducer, moving iron transducers in exam 1. Since then, we've gone through rotating electrical machines, that's DC motors. Primarily, we've barely touched on AC motors. No homework problems on AC motors at all, right? So I think you can read between the lines here. Then what did we do next? We then got into fluid mechanics, or fluid power systems. We had 1 homework on fluid power systems. Then we got into the ideas of feedback, right? And we had mapping out so we had step responses. We had mapping out the complex plane in terms of how pole locations correspond to the step response. And then we got into PID control. A few examples of that. So we had a homework problem on PID control. And that would be kind of the span of homeworks 5 through 8. So anything that's from 3260 or homework 1 is leading up to this. So it would still be fair game. There's going to be a definite emphasis on homeworks 5 through 8. Any other general questions? Yes?
I guess for DC motors, should we be like able to memorize how to derive the equation from that?
So it's open book, open notes.
Oh,
Yeah, so you can memorize it if you want, but and save your brain for other things too. Carson. You will not need one. Yes.
So will we just like need to know we'll have to book, but like the 3 motors, like the series, parallel, and shunt, like those.
Yeah. So in class we went through series, parallel, series, parallel, and shunt are one and the same. Those are just 2 different names for the same exact thing. And then we went through permanent magnet motors as well. The project, right? The project went through permanent magnet motors. Okay. Well, then I'll see you this afternoon for worked out examples, whatever you ask.